good morning, good afternoon, and good evening. Welcome to this episode of the ITU AI and Machine Learning 5G webinar challenge series. Thank you very much for sparing your valuable time to join the session today. I'm sure that by participating in today's webinar session, you will gain useful knowledge as well as ideas to tackle the problem statement that is going to be introduced. My name is Thomas Bascolo from the ITU, and it is my privilege to introduce today's webinar. The AI and Machine Learning 5G Challenge is organized by ITU, which is the United Nations Agency for ICTs. This challenge is currently sponsored by Xilinx, and we are grateful to them for their sponsorship. The challenge aims at creating a community that will solve network-related problems using AI and machine learning. Now, I would like to introduce today's speaker. Today's webinar is going to be given by Shikun Yang. He is an algorithm senior system engineer in network management and service system department at ZTE. He received his bachelor's and master's degree in computer science and technology from Tianjin University. He focuses on solving problems in the field of telecommunications using machine learning and deep learning. In today's talk, he will talk about the combinatorial optimization challenge, especially on delivery route planning optimization. Combinatorial optimization is a very important subfield of computer science, which aims to find the optimal solution under a series of constraints. In telecommunication network, combinatorial optimization plays a key role, especially on the typical problems, which is also part of the challenge, and in global optimization of network resources. By optimizing network resources, it is possible to provide more users with higher speed, more stable network services, as well as help them to have good connection. In order to help participants understand the problem statement, this challenge has omitted the complicated telecommunication technology and give an abstraction, especially on the delivery route planning problem. On the dataset, it is provided the solution that gives the lowest cost with minimum time will thus be the winning solution for the challenge. Now, I would like to call upon Shikun. Welcome and good afternoon.
Hello, everyone. My name is Yang Xikun from ZTE. It's a pleasure to join this webinar. And I really appreciate ITU give us this chance to hold this challenge. And today we will talk about combinatorial optimization. This is a very common and important field. Now, here is the table of content. First of all, let me give a brief introduction to the concept of the combinatorial optimization, including what is combinatorial optimization, also known as CO, as well as several classical combinatorial problems and their corresponding problems in the real world. Secondly, let's talk about the difficulties of solving CO problems. The second part is about deep learning for combinatorial optimization. And the first part is why we use deep learning in CO problems. And the second part is deep learning solutions for some classical problems. The last part is we will talk about the CO problem in telecommunication networking. Here we will talk about a typical application, network planning, and let's talk about this problem, which is the target. It's also the target of our challenge today. We will use a simple sample to explain the task and the goal of this problem, and as well as some details of our challenges. And now let's talk about the first part. So what is combinatorial optimization, aka CO? Here we make a brief definition that the CO is a topic that consists of finding an optimal solution from a finite set of solutions. Here we need to pay attention to 2 points. One is the finite, the solution set is finite, and the second is discrete, it's not a continuous space. And CO is a very important subfield of mathematical optimization, but it not means that it only exists in theory. In many aspects of our real life, we can see the CO has very important applications, just like engineering and manufacturing, transportation, and telecommunication. And the last part is most we are all familiar with. At the same time, the CO is also a big challenge for AI and machine learning and software engineering because computer science has always been closely linked by the mathematics. Now, let's look at some classical combinatorial optimization problems in the real world. And the first one is the traveling salesman problem, which we call it TSP. It is such a problem given a series of cities and the distance between each pair of cities to find the shortest path to visit each city once and return to the original city. Let's look at this graph. The picture, the left part, we can take the cities as the points, and there is a fixed weight between each pair of 2 points. And the right part is about a solution for this problem. And in reality, the problem corresponding to the circuit design, which target is to design the high-performance circuit, reduce the area of the board, and save the cost. The second one is bin packing problem. This problem is easy to understand. That is given a fixed size container by adjusting the orientations, positions, and order of the items, so that the items can be put into the container as many as possible. With the development of online shopping, the transportation service is becoming more and more important. To place as many goods as possible means to transport as few times as possible, which means more cost to save. And the last one is the graph coloring problem. This problem is also easy to understand. That is to use the least color to color each node of the graph. Make sure that any two connected nodes do not have the same color. In real world, this problem is also closed-class, just like the coarse arrangement and the mobile frequency assignment, which try to avoid the frequency interference. So both of them are very practical problems. And although those problems are close to our lives, and they are not easy to solve, many of them are hard to solve. And I think the key point is the size or the scale of the problem. When the solution space is small, we can use some classical algorithms, just like dynamic planning and so on. As the scale of the problem increases, the number of solutions will increase rapidly. It's also impossible to traverse the entire solution space. Let's look at these tables. This table is about the relationship about the nodes and the possible roots of the TSP problem. And we can see the first row is the node's number and the second row is the possible roots. In this table, we can see that the possible roots is the factorial of the nodes. When the nodes is 5, we can see that the possible root may be 120, and the 7 is 50, almost 5,000. But when the nodes increase rapidly, we can see that the possible roots also increases rapidly, and it's almost impossible to make the searching in the limited times. So in this situation, we can only use some heuristic algorithms to get an approximate optimal solution, just like genetic algorithms, simulated annealing algorithms, and so on. But the biggest problem is these algorithms are time-consuming and low efficiency. So because of all these problems, we turn to use the algorithms of machine learning or deep learning to solve the combinatorial optimization problems. In recent years, with the deployment of the deep learning, more and more problems can get better solutions. For example, the famous AlphaGo. This achievement gave us confidence to try. So what is the advantage of AI, especially deep learning? So why we use deep learning in CO problems? I think this is two parts. The first one is the deep learning model is a high dimensional problem solver. CO problems are always accompanied with many variables and constraints, just like we talked before. And the deep learning model gives an approximate function with a large number of parameters which can be optimized and get a good solution on most cases of the data set. At the same time, as an end-to-end solution, a deep learning model lets researchers to focus on is a learner, but not a searcher. It means that a deep learning model can get knowledge from data, just like supervised learning, or from reward, just like reinforcement learning. And it influences the solution from the knowledge learned, rather than searching into the solution, the whole solution space. So if the thing of the problem has a little change, our deep learning model can be used in this situation by a little transfer learning, or maybe it can be directly used into the new thing if the new thing is similar to the original thing. So without the time-consuming searching, the deep learning model will be faster. With the support of GPU, the inference process can be further accelerated. Okay, now let's talk about some deep learning solutions for the classical problems we mentioned before. And the first one, let's go back to the TSP. This work is from Oreo Venus et al. And they do a clever modification on sequence-to-sequence model and attention model. So they propose a model called pointer network. Let's look at the picture on the right. We can see that the input of the model is the coordinates of the cities, but the output is no longer the weighted average of the city's coordinate. Instead of this, the output make a pointer. They point to the index of the input. So with this change, they change the model from fitting coordinates to selecting an index. So it greatly reduced the learning difficulty. By the supervised learning with a generated data set, this model achieves the same level as the traditional algorithm in the 50 nodes TSP, and even better than the traditional algorithm in some scenarios. And the second example brings us back to the 3D bin packing problem, as we mentioned before. This problem doesn't like the TSP. It has some difficulties in here. The first one is the solution is a series of complex decisions, just like we need to determine the order, determine the orientation, and the position of the items. The second one is it has many constraints, just like it cannot exceed the size of the bin. So Hao Yanhu et al. Proposed this framework of reinforcement learning. They take this framework into three parts. The first part is about a pointer network to generate the item sequence, and the second and third part are all heuristic algorithms to generate the item orientation and the computed list surface area. They do a clever change to make the target to minimize the surface area of the bin, so it can simplify the problem. Okay, and so because the author is from a company of transportation, so they do some customer analysis and get the item number of 8, 10, 12. They all based on the number of items in one customer order. So some experiments show that the algorithm achieves a better result in this scene of 8, 10, and 12 items. And before introducing the next example, let's talk about some useful tools for graph feature extraction. As we know, in image processing, the convolutional neural network can extract image features but the graph structure is not as regular as the image. So CNN is not suitable here. And graph embedding technology solves this problem. Let's take a look at the graph on the left. Here is the example about graph embedding. So when we use graph embedding, it's converting a high-dimensional sparse graphs into low-dimensional, dense, and continuous vector space, preserving maximally the graph structure properties. So with the development of graph embedding, we can see a lot of great methods, just like deep work, node to vect, and the struct to vect. With the graph embedding, we can use the graph to a lower space, just like text embedding in NLP domain. Another tool is graph convolution neural network. It can be used directly as a classification model to do a graph classification. It also borrows the idea of convolutional neural network. Another usage is it can be used as a part of model to get graph embedding and extract the graph features. We talk about these two tools. We want to let the challenges can read this, and with these tools, it maybe can help to solving our challenging problem. Okay, let's talk about the graph coloring problems. We talk about it again because it's similar to TSP. This problem has a very large solution space. Jia Huang et al. Proposed a faster color night based on the AlphaGo Zero framework. This framework takes into the following part. The first part is graph embedding. They use graph embedding method to get the graph features, just like we mentioned before. And in the second part, taking a node as a starting point, they use a deep reinforcement learning model to calculate the probability of the color on the next node and select the most likely color. Here, the author designs a complex model which combines the color information and the node information together. And it also borrows the idea of the pointer network. After doing this, they put the color of the deep learning model inferenced to Monte Carlo tree search to get a better solution by searching. And at the last part, they use the self-play. So the baseline during this situation, baseline is updated constantly and then used to iteratively improve the performance of the target network and finally achieve better results than the traditional algorithms. And after discussing these examples, let's talk about the application of CO in telecommunication networks. In this field, I think the most typical problem is network planning. And as we know, the 5G network brings many innovations, including higher speed, higher bandwidth, lower delay, and so on. But at the same time, it also brings an explosion in data traffic with more users and more services. So a good network planning can not only bring high quality network services to users, but also save bandwidth resources, which will reduce the telecom operators' cost greatly. And network planning is a big and systematic project, including many aspects. This time, let's focus on the one of the typical scenario, which is also our challenge topic, user service planning and deploying. And the goal of our challenge can be summarized as deploy all services to minimize the overall delay and the network resource constraint. Let's explain this on a simple example. Suppose we have a network of 4 nodes that R1, R2, R3, and R4. The length is shown in the left figure. The bandwidth of each link is 5. The number on the link means the delay when the services pass. We also have 4 services from S1 to S4. They all from R1 to R3. And the required bandwidth of the services are 1, 4, 3, and 1, represented by blue, red, green, and yellow. The figure in the middle and the figure on the right are showing 2 solutions of planning. In the middle one, S1 and S2 pass R2 to R3, and the delay is 5 because no more bandwidth left in R1, R2, and R3. So the S3, S4 can only be passed R4. And the delay is 6, so the total delay is 22. The solution on the right figure is different from the last one. The S1, S3, and S4 services are all designed to pass R2, and the resource just enough. The S2 with the largest bandwidth is deployed to R4. And the over delay totally is 21, which is less than the last solution. Therefore, we said that the solution in this situation, the solution is in right figure is better than that in the middle. And although the goals and tasks of our challenge are simple, but the real scenario, the networks becomes more complex. For example, there will be multiple channels in between 2 nodes. In order to make us easier to understand, we have omitted the complete telecommunication technologies and abstracted as a delivery route planning problems. Okay, we can see the problem statement from this link. And for now, we put this on the wiki of Adelic, and as we will put it on the official website of ITU as soon as possible. As about the solution, We are not limited to deep learning method. Any other algorithms which have excellent performance can be used, even if we talk about a lot of advantage of deep learning models. In our challenge, all type of algorithms can be accepted. As for the dataset, we will upload to the problem statement website soon, so we can download it from there. The format of samples are as follows. Each sample has two parts. The first part is the graph definition. It's a JSON object. We can read node info and link info from it. The second part is delivery definition. It's about an array of tuples. Each one contains starting point, end point, and weight. Here are two tips. The first one is our data is divided into public and private parts. The public parts is provided to challengers to train the model and validate the algorithm. In the final evaluation, both public and private parts are used, so it can prevent the algorithm from overfitting. The second one is the amount of the data we provide is not very large, but we have specified a scale of the problem in the statement. So our participant can generate some data ourselves that meet the requirement of the problem. And this may be a good method of data enhancement to bring good result. As about the submitting, it will be same as last year. We still use GitHub to collect the results and the solutions. We need the challengers to create a private GitHub repository to contain their work. And add ITU AI Challenge DTE this as a collaborator. The repository must be made public before submission deadline, and it should be accessible till the end of the final event of the ITU challenge. And the repository should be contains these things. The first one is the runnable source code, so we can run it on the public and the private data set and check our result. And the second one is the result and the running time of all the samples in dataset. So we can run it and compare with this information. The last one is a description document, just like a README or instructions describing how to verify the result with the source code and hardware configuration, explanation of the algorithm, and any other things you want to say about the challenge. As for the evaluation, we will consider the following aspects. And the first one is performance of algorithm accounts for 60%, and both total cost and the running time will be taken into account. The second one is solution advantages, which accounts for 30%. We will consider whether the solution is reasonable and whether the solution has enough practicability, innovations, and universality. And the last part is completeness, accounts for 10%. We will check whether the requirements of challenges are fulfilled according to the proposed scheme and design. The last part is about some tips for the challengers. The first one is all of this about the timeline. The first one is registration. Register for the problem statement. You can enroll as a team with 1 or 4 members. The registration is open from June 9th, 2020 to August 31st, 2020. And the submission, we will begin to accept submissions from July 1st, 2021. And the submission deadline is October 25th. Please submit by adding the ITU AI Challenge DTE as a collaborator of your GitHub repo containing your solution. The evaluation will be for the November 10th. The final tips is about global round. Winners of the problem statement will take part in the grand challenge final of ITU AML, the 5G challenge, and compete for the final awards. Okay, that's all I share today. Thank you for listening. If you have some questions, please feel free to ask. Thank you.
Thank you so much, Shikun, for making this nice presentation about combinatorial optimization. This is quite an interesting field, interesting area. And yeah, it's time for the Q&A. So I would like to invite my colleague, Vishnu. Vishnu, good afternoon.
Hi, Thomas. Hi, Shikun.
Hi, Mr. Ran.
Thank you. Thank you. That's a very interesting problem statement. I want to ask, I was looking at your task. So if you look at your website, I was looking at your task. And I want to ask, is there a mapping between the transportation network that you describe in the task? For example, the routes of the delivery, the lanes, and the nodes, that task, the features of the task. Is there a mapping between that and the service? Yeah, right here. So is there a mapping between the task and the service deployment problem that you describe in this slide? Is there a mapping at all, or is it totally different?
I think it is very similar of these two problems, so we can extract it as a delivery problem. So we can see that the delivery map and the telecom network, we can see they are the same thing. They all have nodes and links, and the lengths in the transportation. We can see that as a channel in the links, and the node we can see that is a middle station, and the services we can see it as the goods we want to transport. So all these things we think is a very similar problem. So but in telecom technicals, we can see that many technical issues, just like we need to know the radio, the channel, and so many things. So if we put it on the road, put it on the transportation problem, it is, I think it's easier to understand. So we omitted all these technical method or technical things and put it into a simple, I think it's a simple, it's a simple description of this hard to understand thing. Yes.
Thank you. Thank you. I think there are some questions about the data set. Do we have one graph network that is divided into training subgraph and testing subgraph, or is it a set of independent graphs? That's the question.
Okay, this will be a small set of different graphs. Each graph is not similar, but it's not same as others. They all in a limited of our problem specification. Just like the node number cannot be exceeded 300, and the length, which means the channels cannot exceed 40, and the goods weight, and that means the bandwidth of the service cannot be exceeded 10. All of these are similar, but not definitely different. Okay.
Thank you. Thank you. Yeah, I think actually I had something similar. So you told us that we could use the participant could generate the data, right? So In case as a participant I generate the data, would the same, I have to use the same same features that you just now described, the same conditions. So if you look at that, if you look at the website, it says that 300 transportation nodes, no more than 10 other nodes, etc. And there is a condition of no more than 40 lanes. So if I generate the data, the question is, the same conditions should apply for my data as well?
Yes, I think this problem is describing a situation more than a particular data. And so when we want to solve this problem, I think it is will be defined in a small scope. It must be defined in a scope. So we write it down this constraint in our problem set. So if you generate under this constraint, I think we can take it as a right generation data, generated data. If it works in this situation, the algorithm will work in the situation we want. So we think that is a good solution. Yes.
Okay. There is a question again on data sets. How big are the topologies? Number of nodes and edges. I think this is already there in your website, but could you please describe again?
Okay, the nodes is no more than 300, and the length is no more than 40. And the deliveries number is limited to 1,000.
Thank you. And I think there is a question on, can we have more than one link between two nodes?
In our problem, the link is the unique, but in this link, we consider it as a road. It has some length. Each length we can see that as the channels in the link in our telecommunication domain. So the link is unique, but the channels is multiple.
Thank you. So you mentioned other type of solutions are possible. I think other than deep learning, we can also have heuristic solutions, right? That's as what you meant. So in case of such heuristic solutions, how do you validate these solutions? So what I'm thinking, so let's say you allow the data set to be generated and then apply heuristic solutions to come up with a solution using that data set. I'm wondering how you will validate the submitted solution in that case.
Okay. Even the participant can generate data themselves, but we have a private data set for testing. Some of them is we generated according to our real situations. Some of them we have to take some hard examples to solve to check the robust of the algorithms. So I think in each public data set or private data set, each samples we have a score. If we use this score, it is a good metric to get the performance of the algorithms. Yes.
So if I use my own data set, should I submit it to you back, or it doesn't matter and the evaluation is completely done based upon your data set?
Okay, if the dataset generation is complex, and you can upload it to us. If the dataset is so big, so you can give us the generate algorithms or generate method or generate functions to us. We can run it and generate data and test your program.
Okay, that sounds good. I think I had a couple of more questions, which is I don't see any questions in the Q&A. So if there is any question, please ask. And there is a website which Leah put in the chat. Please check that. I was checking that just now. There is a detailed description of the problem statement and the data set in that website. So please, I suggest the participant to check that data website. Can I ask you about the type of problems? Right, in this particular case, you are basically having a very particular solution. I mean, problem boundaries, but in general, as you told in your initial slides, what kind of problems? Yeah, around there you were talking about the type of problems which can be solved. And I remember that there is you know, I was looking at this long back, and that I may be wrong here, but I think there are different sets of problems which are maybe NP complete and maybe not. So which type of problems are possible to be validated here, and which type of problems need time complexity in modeling? Yeah, so that's my question. So in terms of complexity in modeling and evaluation, whether with respect to correctness and completeness, what type of problems we can apply this CO solution? What is your opinion?
Okay. In my opinion, we want to solve a series of problems. As we mentioned before, the service planning and deploying is only one of them. In the service planning, if we planning the services as good as possible, we can reduce the delay and reserve more empathy resources to enlarge the network or add new services and new users. So the efficiency of the network will be grow higher. That is the one thing. In many other aspects, just like the base station and the base station planning or the base station deploying is the same. Also the same scenario too. So we also use the CO method to do these things. So this problem is also a concept model, or we can say that is a prototype. We want to use it in the ideal situations, but when I use it, we can use it in many practical aspects. Yes.
Mm-hmm. Thank you. I see that. Okay, so then one question that I had is regarding, you had some examples about mapping these particular problem instances like traveling salesman and graph coloring, and these you had couple of slides on how it is mapped to deep learning approaches. Yeah, right here. So I think this this mapping between from from real problems like traveling salesman and bin packing or knapsack problems and graph coloring. There is, it looks to me a little heuristic by itself. I mean, the mapping itself looks a bit heuristic. How what is the approach to do the mapping? There is if I look at explaining the mapping, I'm finding it very hard to explain the mapping. I think in the next couple of slides, you are showing the examples of the mapping of TSP, mapping of bin packing, and so on, right? So how do you explain this mapping? And is there only one way? I don't think there is only one way of doing this, right? This is probably one of the best ways of doing it. But what is the way in which one would, if I take a new problem, then how would I map it? What is your opinion?
Okay, I think just like you say, it's only mapping one mapping in the real world, but in our situations we can find many things. If we dig into it deeply, we can find some. There will be a mathematical model in it. For a particular mathematical, you can use many methods to solve it. The CO method is only one of them. You can use CO. You can try to use CO to solve any other problems. But when we evaluate this, we can use some basic feature of it, just like we said in the first slide of the definitions. If it has a finite discrete solution set, and we want to find an optimal one from it, you can try to use CO method to do this. I think this is an entry point. In next step, we can do more analysis, whether we can use it just like the data scale, the problem scale, if it's simple or complex, to do this, to guide us to do the CO algorithms, or use another algorithms to do this. Yes.
Okay, but what about the next step? So if I classify the problem as a C, or rather, if I identify the problem as a CO, I am able to model it as a CO, but now I want to apply deep learning to solve it. There it is not, there is no standard approach. It looks like, say for example, I want to do now feature engineering on this CO problem of TSP. How do I do that?
Okay, I think there may be not a standard procedure or standard method to do this. I think the feature engineering and the feature extraction, just like you say, need some of imagination and some experience to do this. When we solve any other problems, I think they all need this. Only the experience and the recognition of the things and some other technicals is common, but there may be not a standard procedures to do this. If you are a deep learner, you can use the deep learner procedure to solve CO problem, just like data cleaning, data featuring, and modeling, and the training and the inference, just like this this workflow to do this. Even if you are a machine learner, you can use some just like fitting regression and other classical algorithms to try and to find suitable algorithms to solve the problems. Yes.
Okay, thank you. There is a question on intellectual property policies, but that I will leave it to Thomas and the Secretariat to handle that. Also, it will be clarified in the website, in the challenge website. It's not anything specific to this problem statement, I think. Let's check if there is any other question. I think not. In that case, I want to thank Shikun for the time and the patience in answering all the questions. Once again, I think a lot of details is there in the website. So please go to that website and check. And it looks like a quite comprehensive thing. The data will be released next week, right, Shikun?
Yes, we will provide the data as soon as possible. Maybe next week we can align it.
What about the next steps? So now you have this challenge, you have this competition. Can I ask you, what are you planning about the next steps for after this is done? Would you look at say prizes, internships, or something like that? Is ZTE planning ZTE planning something like that, or are there papers which the participant can, or the winner of the competition can write some papers based on this? Are you planning something like that? Could you or maybe in terms of applying this back into the network, into your research, especially in the context of the mapping to telecom domain, like service deployment domain, like you were explaining earlier. So what is the next step after this challenge? Can I ask you, please?
Yes, just like you say, we find this problem is a hard, but really a hard problem and really a valuable problem. So we want to use it into the real networking engineering, and we are network telecom operators or telecom manufacturers. So we concern the implementation more than the high level score or the top one solutions. So in our opinion, or when we consider evaluate the solutions, we think both sides of the solutions, the reasonable and the time consuming will be as important as the final the cost result. So if you have a solution that's not using the meanest cost, but it has a high efficiency, just like a very short time, it's also very valuable to our implementations. So we will not only consider the top one, we will consider all of the solutions and finding maybe find some good solutions, and we will optimize it or change it or modify it to use in our real life or real engineering. And we will seek some new ideas from these solutions. Maybe these competitors can enlighten us to get a new way or a bright way or to solve the question, solve this problem, and get more new problems to see or to discover. Yes.
Okay, thank you so much. Yeah, that makes it complete. Thank you, Shikun, for that patient explanation for all the questions. It's a really interesting problem statement, I should say. And as you say, there is a lot of applicability in the network. As you say, there is a way to come up with innovative solutions which can make a difference in the network. So thank you so much, Leah. Thank you, Shikun, for that excellent problem statement and answering all the questions. Back to you, Thomas.
Thank you so much. I would like just to address the question that was asked first about the IPR. As you have seen in the chat window, Reinhard has posted the IPR related discussion for the challenge. You will find this text on the website. We are going to update the website next week, hopefully, and all this text will be available on the website. But in short, the participant or the submitter will retain the IPR for the solutions of the problems that are going to be submitted in the challenge. So all the problem statements that we have, if you're going to submit the solution, you're going to retain the IPR. So this is the short way to respond to that question. At this moment, I would like to give a very big thanks and to show appreciation to Shikun for the wonderful talk on Combinatorial Optimization Challenge, Delivery Route Planning Optimization. We are very happy that ZTE, Shikun and Leah teamed up to give us this problem statement, and we hope that all participants, you can start working on it. We have shared the link of the website where the challenges or the problem statement is hosted. So please head there and register, as well as start working on the problem statement. I would also like to thank everyone for attending today's episode in the webinar series brought to you by the ITU AI and Machine Learning 5G Challenge. We have more webinar sessions that are coming up. The next one is on 14th June, which is the next Monday. So please check information that is shared in the chat window, as well as you can see on the event page, AI for Good event page. You can see all the events that are scheduled to happen in the next few weeks. From me and my colleagues at the ITU AI and Machine 5G Challenge, I would like to wish you a very good day and bye-bye.